Okay, everyone. So yesterday in the class, I uploaded the lecture that I recorded, but for some reason, I used my iPad horizontally, and when I recorded that, it uploaded that vertically, so some of the materials weren't shown properly. So I'm going to record another lecture that covers all the materials that I talked about yesterday, so you can listen to this lecture instead, so have the whole picture of everything that I talked about in the class yesterday. So, first, I'm going to talk about exams. You had exam 1, exam 2 so far. And I realize that some of you might have low grades on those. Imagine you got like 20 on exam 1, 30 on exam 2. So, for exam 3, if you get considerably higher grade than the other two, which means that at least 20 points improvement. Imagine you get like 80 in the third exam, I'm gonna omit the lowest grade and consider 80 for that exam as well. So you still can have a really high grade in the exam and in the course overall. So if you had like, exam 1, exam 2, exam 3, if you got like 100 on exam 1 and then 90 in exam 2 and then 80 in exam 3, I'm not gonna omit your high grades. This is only to help you improve your grade, so it's not gonna hurt you and your grade in any way. And if any of you have any issue with this or don't like this, just email me and then I discuss this with you. I'm doing this to improve the grades of who are suffering, but not hurting grades of people who are not suffering, if that makes sense. So this is about the grades. So still, even if you're failing class so far, you have the opportunity to pass the course and even get high grades. And if I see, improvement in the class so much, I may consider ways to even improve your grades even more. But first I should see if this strategy makes any progress in your grades in first place. So I'm going to talk about mass percent composition from a chemical formula. So last week, or rather last session on Monday, on Friday, today's Tuesday. On Friday, the last session that you listened to the lecture, we talked about mass percent composition. And we said that this is kind of an experimental value that we will be given. So for instance, we say that sodium chloride is 39% sodium by mass. It means that mass percent composition of sodium in sodium chloride is 39%. And we define the formula that mass percent of element X equals mass of X in a sample of compound divided by mass of the sample of the compound multiplied by 100%. So basically, when you want to know, for instance, mass percent of sodium, you calculate or basically it's equal mass of Na divided by mass of NaCl multiplied by 100. And when you do this calculation, your answer would be in percent. And we gave an example that if you basically example 6.8, we said that, we went through the example that I gave in the beginning of the chapter that we should consume 2.4 gram sodium per day. And the problem, basically in example 3.8, we are given that, the mass percent composition of sodium in sodium chloride, basically mass percent of sodium in sodium chloride is 39%. And then we want to find how many grams of sodium chloride we should consume to satisfy this condition. So basically how many grams of sodium chloride. So we just, say how many grams of sodium chloride equals to 2.4 gram of sodium multiplied by gram of sodium, gram of NaCl. And I told you this is kind of the only time that we work with grams directly if we are given mass percent composition as such. So it means that in 10 gram of sodium chloride we have like 39 gram of sodium. So 2.4 multiplied by 100 divided by 39 would be 6.2 gram of sodium chloride. Now imagine if we don't have this 39%. Imagine I give you a question in the test that calculate mass percent composition of sodium in sodium chloride. We are asked to calculate how many grams of sodium exists in 100 gram of NaCl. And this is something that we went through for the past week and past few sessions, like 3 sessions, that we say how many gram of sodium equals 100 gram of NaCl. And then we say that, so I'm going to write that smaller so I can fit everything. Say how many grams of sodium equals 100 gram of NaCl. And then we multiply that gram of NaCl to mole of NaCl. And then mole of NaCl to mole of Na. And then mole of Na to gram of Na. And then we go look at the back of the book. NaCl equals 22.99 plus Cl, which is 35.45. And if you remember, we have like Na 22.99. We have Cl 35.45. And then this is plus sign. This is roughly 2358.40. Instead of 5, I said 4 because this is like 0.01 less. It's gram per mole. So 1 mole of NaCl has like 58.44 gram in it. 1 mole of NaCl, 1 mole of Cl, 1 mole of Na. You have the number here, 22.99. And when you do this math, it would be 100 multiplied by 22.99 divided by 58.44. That number would be 39.339, which is almost 39. So it means that in 39 gram of Na, basically in 100 gram of NaCl, 39 gram of Na exists. It means that mass composition of sodium chloride is 39%. And if you were in the class, I would ask you, do you have any questions so far? But since you are not in the class, I just assume that you will email me if you have any question about this. Your book gives a way to just calculate this without this writing these conversion factors. Basically, mass percent of element X equals mass of element X in 1 mole of, I'm gonna again start over. I'm just like writing too big to fit everything. Okay, just say mass percent of element X equals mass of element X in 1 mole of compound divided by mass of 1 mole of compound multiplied by 100%. So remember, if you calculate mass of element, a specific element that you want to calculate in 1 mole of compound, divide that by mass of 1 mole of compound multiplied by 100, it gives you in percent, mass percent of element X. So in the previous example, I say mass percent of Na equals mass of element X in 1 mole of compound. So in 1 mole of NaCl, we have 1 mole of Na, and 1 mole of Na weighs 22.99. Divide that by mass of 1 mole of compound. 1 mole of NaCl basically weighs 58.44. Multiply that by 100%. Probably I can just write this 100% much closer here. And then if you do that, you get roughly 39%. But you see, this is kind of like the same thing as here. You have like 100 multiplied by 22.99 divided by 58.44. So basically, if I can use my blue here, this and this are the same, as you see. But here in the definition, remember that you in 1 mole of compound, you should report mass of that element. So if you had, like, for instance, CCl2F2, in 1 mole of that, you have like 2 mole of chlorine. So I'm going to go through an example so I clarify what I mean with that. And I'm going through an example that your book gives. It says, calculate the mass percent composition of Cl in I'm just gonna write this better. In chlorofluorocarbon CCl2F2. So So if you just write the above formula, we have mass percent of Cl equals mass of Cl in 1 mole of CCl2F2 divided by mass of 1 mole of CCl2F2 multiplied by 100%. So first, we calculate molar mass of CCl2F2. So you remember you have 1 carbon plus 2 chlorine plus 2 fluorine. Oops, that one I use. 2 multiplied by fluorine equals 1 multiplied by, and maybe I write this for you too. So you have like, you go to your periodic table, you have like carbon, which is 12.01. You have like chlorine, 35.45. You have fluorine, 19. So you can write molar mass of CCl2F2 equals 1 multiplied by 12.01 plus 2 multiplied by 35.45 plus 2 multiplied by 19. And then when you do that, you get the number to be 120.91 gram per mole. And it means that 1 mole of CCl2F2 weighs 120.90 gram. And you just substitute in the formula mass percent of Cl equals mass of Cl in 1 mole of CCl2F2. In 1 mole of CCl2F2, we have 2 moles of, Cl. So we have like 2 moles of Cl, which is 1 mole weighs 35.45. So 2 multiplied by this much would be mass of Cl in 1 mole of CCl2F2 divided by this molar mass that we calculated here. Basically the weight of 1 mole of CCl2F2 is 120.91. So this is gram, and then when you do multiply by 100%, when you do the math, it would be 58.64 100%. So this is the first way to solve this problem. The second way is just like do the stoichiometry, basically do the conversion factors that we were doing. You say how many, remember, I'm going to write this down. Finding mass percent of Cl is equal or equivalent to answering this question: how much in gram Cl exists in 100 gram of CCl2F2. So you can say how many gram of Cl equals 100 gram of CCl2F2. And then you say gram of CCl2F2, you convert that to mole of CCl2F2, and then you convert mole of CCl2F2 to mole of Cl, and then you convert you convert mole of Cl to gram of Cl. And then this one we calculated just above it, 120.91. 1 mole of CCl2F2 has 2 moles of Cl in it, and 1 mole of Cl here is like 35.45 gram. So your answer is 100 multiplied by 2 multiplied by 35.45 divide by 120.91. So after doing this calculation, you realize that this that I wrote here is equivalent to this. It's basically 100 multiplied by 2 multiplied by 35.45 divided by 120.99. And the answer is 58.64. So this means that in 100 gram of NaCl, 58.64 gram of Na exists. That is equivalent to mass percent composition of sodium in sodium chloride is 58.64%. So if you write the problem, if you solve it like this, you can write this conversion factor here so you don't miss that. But in the formula that we wrote here, if I manage not to mess these things up, in the formula that we wrote here, it is possible, oh my god, I'm just like messing this up so bad. Okay, maybe I managed not to mess things up so much. Let's see. Okay, but in the formula that we wrote earlier, I'm gonna just write this again because it would be a review for you, and then I make sure that. Okay, so we know the mass percent of element X equals mass of element X in 1 mole of compound divided by mass of 1 mole of compound multiplied by 100%. So if you use the formula, remember this is mass of element in 1 mole of compound. So you should see in 1 mole of compound how many moles of that element you have and multiply that by atomic mass unit of that specific element. But if you follow just like the conversion factors that I write here, that manifested itself in the solution itself, so you don't have to worry about it. Basically, in order to cancel that out, you should write this true. But you may forget it if you write the equation as like this. So now that I'm gonna take off my jacket so I have like more flexibility moving around. So now that I'm recording this, I'm going to go through more examples because I'm not restricted to like 50 minutes. Example 6.9. Calculate the mass percent of Cl in ferrion 114, basically C2Cl4F2. So you have two ways to solve these problems, whether you use the formula or find the mass of Cl in 100 gram of C2Cl4F2, and they are exactly equivalent. I'm just going to use the formula. First, you calculate molar mass of C2Cl4F2. So that is 2 multiplied by C plus 4 multiplied by Cl plus 2 multiplied by F. And then you go to a periodic table. You have carbon listed at 12.01. You have Cl listed at 35.45. And then you have F as 19. So molar mass of C2Cl4F2 equals 2 multiplied by 12.01 plus 4 multiplied by 35.45 plus 2 multiplied by 19. And when you do the math, you find this number to be 203.8 gram per mole. Okay, just making sure that it's recording my sound. Yesterday I was holding office hours, and then I had I was broadcasting with my iPad, and I had my video on my laptop, and the sound didn't record. So just checking that if it's moving, and it seems that it's recording. Hopefully everything will be fine with this lecture. It means 1 mole of C2Cl4F2 has 203.8 gram in it. So, and then I told you that the chemical formula can give you information about mole. So I write this like this: 1 mole of C2Cl4F2 has 2 moles of C and 4 moles of Cl and 2 moles of F. So you see that you have 4Cl, 2F. Now, just calculate the mass percent. As easy as that. You say mass percent of Cl equals mass of Cl in 1 mole of C2Cl4F2. But 1 mole of C2Cl4F2 has 4 moles of Cl in it. So we write it 4. Multiply by. If you go to your periodic table, I write this here, so I don't want to scroll up. Cl 35.45. 1 mole of Cl has 35.45 gram of Cl in it. And then divided by mass of 1 mole of your compound. 1 mole of your compound has 203.8 gram on it. So 4 multiplied by molar mass of Cl, which is 35.45, divided by 203.8 gram, which is molar mass of your compound, multiplied by 100%. That gives you 39.58%. So I hope this is clear now, the mass percent composition. Whether you will be given the experimental value and then you convert between grams, or you would be asked to calculate mass percent composition. So next part, Next section, 3.8, is calculating, if I can write, calculating empirical formulas for compounds. So you remember the difference between empirical formula and molecular formula. I'm just going to write it. Empirical formula. And I mentioned that in the class that I'm going to give you examples in the exam, ask you questions about these concepts because they are really important. Empirical formula gives the smallest whole number ratio of each type of atom in a compound, not the specific number of each type of atom in a molecule. And molecular formula is always a whole number multiple of the empirical formula. Basically, molecular formula equals empirical formula multiplied by n, where n equals 1, 2, 3, and so on and so forth. So what it means is that, empirical formula gives you the ratio between the atoms. Imagine you have like C and H. And then if I write, here CH, you can have the ratio between atoms. You can have like 1 to 1, 2 to 2, 3 to 3, 4 to 4. You can write CH, C2H2, C3H3, C4H4. All the ratios are the same. But empirical formula gives you the smallest one. So only this is an empirical formula. Let me see if I can do this. Okay. So only CH is empirical formula. These three are molecular formula. Why? Because 2/2 is not the smallest whole number ratio. 3/3 is not the smallest. So if you write a formula and you can simplify it, that is not empirical formula. In other words, let me give you some examples. If I can just scroll down. Ooh. Okay. Imagine, where did my black go? I'm trying to... I should see... Oh. Where are my colors? Okay. Maybe I just pause the video to figure this out. Okay, turned out it wasn't that difficult. So if I write for you H2O2, C3H6, CH C6H12O6, C2F6, or like CCl2F4. I'm just like writing random combination of atoms and molecules. So you see how I have 2/2, this ratio. Can it be simplified? The answer is yes. I can write is 1/1. So basically I can write HO. If this is 3/6, can it be simplified? Yes, because it is like 3/6. I can write that 1/2. I can write that CH2. This is like 6/12/6, basically the ratio of the atoms. Can it be simplified? Yes, I can write this as 1/2/1. It can be CH2O. Can it be simplified? 2/6? Yes, I can write it 2/6, which is like 1/3, can be like CF3. This one, can it be simplified? 2/2/4? Yes, I can write this 1/1/2. I can write this as CClF2. So none of these are empirical formula. All of these are molecular formula, and all of these are empirical formula. You may ask, can I write like I can write HO as like H half O half? What about this? Is this an empirical formula? The answer is no. Is it a molecular formula? This is a molecular formula? No, because both empirical formula and molecular formula should be whole number. So if you have something like this in the exam, you should multiply both sides by 2 to find whole number, HO. Okay, and this is like the difference between empirical formula and molecular formula. And now we learned that we can find out from like chemical composition, we can find mass percent composition. Now the question is that can we do the reverse action? Basically, we were given chemical formula before and we calculated mass percent composition. The question is that is reverse possible? And the answer is that yes, we can calculate empirical formula from mass percent composition directly. We can calculate empirical formula directly from mass percent composition. But to find molecular formula, we need more information. And that information is molar mass of the compound. And I'm going to explain to you what all this means. But you remember, when I write H2O, we say from the chemical formula, if I tell you calculate mass percent composition of oxygen in water, what you do is that whether you write your formula that I wrote before, is basically its mass of oxygen in 1 mole of water divided by mass of 1 mole of water multiplied by 100%, or write your stoichiometry and basically your conversion factors, and then you say how many moles of oxygen, how many grams of oxygen equals 100 gram of water, and then so on and so forth. We just went through the problem. I don't want to make this lecture that long, so you know how to do it. But you say that 1 mole of water has 1 mole of oxygen, 2 moles of hydrogen. Now we want to know, can we do reverse? I tell you, we have this much gram of hydrogen, this much gram of oxygen. What is the chemical formula? So we can calculate the simplest ratio of the atoms. It means empirical formula, but we cannot do, for instance, I can find H2O if I'm given how many grams of hydrogen and how many grams of oxygen I have, but I cannot find H4O2. I cannot find this from this directly, unless I have been given more information, and I'm going to talk about those. Okay, basically we want to calculate an empirical formula from experimental data. And I just write the book's example. Suppose we decompose a sample of water in the laboratory and find that it produces 3 grams of hydrogen and 24 grams of oxygen. How do we determine an empirical formula from these data? So remember, when you want to find empirical formula, you should find moles, because in chemical formulas we can have a relationship between we can have a relation between different atoms and how they connect basically with each other, how many atoms of each compound, how many atoms of each element we have in a specific compound with moles. So when you are asked to calculate empirical or find empirical formula, simply calculate moles. So we are given 3 grams hydrogen, 24 grams oxygen. We want to find their moles. I say how many mole of hydrogen equals 3 grams of hydrogen. How many moles of oxygen equals 24 grams of oxygen. And then multiply that by a conversion factor that relates gram to mole. And if you go to your periodic table, you have like hydrogen 1.01, oxygen 16. 1 mole of hydrogen is 1.01, 1 mole of oxygen is 16. And then when you do the math, this is 2.99, almost, oops, it is 3.99, roughly 3 mole hydrogen. This would be 1.5 mole of oxygen. So your formula would be H3O 1.5. So this is kind of like your pseudo formula. It is not still finished because this is not a whole number. If it's not a whole number, your calculation is not finished yet. So you multiply basically, or divide rather, both sides by the smallest number. So I'm gonna just write this. If I can manage to do this. What am I doing? Okay. H3O 1.5. After finding the exact numbers, always divide by the smallest number. In this case, 1.5 would be H2O. So this is your empirical formula. So I'm just going to go ahead and then finish this chapter and then go through some more examples. So now 6.9, we want to calculate molecular formula. Calculating molecular formulas for compounds. I told you molecular formula equals empirical formula multiplied by n. And n is a whole number, 1, 2, 3, and so on and so forth. Now the question is that, imagine I gave you a problem, and then you calculated empirical formula. Can you find molecular formula? The answer is yes, and I just gave you the answer like 10 minutes ago. That if you are given molecular, basically molar mass of the compound, you can find molecular formula. So basically, you can write molar mass equals empirical formula, molar mass multiplied by n, and n is 1, 2, 3, and so on and so forth. So correct. If you are given molar mass, you calculate empirical formula molar mass yourself and you find an n. So this n can be like fraction. It can have like decimal points, but you round it to the nearest whole number and then use that n to multiply by empirical formula to have molecular formula. So in your questions, problems, you find n that is not exactly a whole number as we did just like 5 minutes ago, but you round that number. So basically based on this, your n equals molar mass divided by empirical formula molar mass, and when you do that you find your n and then you round n to the nearest whole number to multiply that by empirical formula to get molecular formula. And I'm going to give you an example. Imagine let me write a example from your book. It says naphthalene is a compound containing carbon and hydrogen that is used in mothballs. Its empirical formula is C5H4 and its molar mass is 128.16 gram per mole. If I just can do this, okay. What is its molecular formula? So almost in all your problems, you should calculate molar mass. So we automatically go molar mass of C5H4 equals 5 multiplied by C plus 4 multiplied by H, and then you go to your beautiful periodic table. You see C is 12.01, H is 1.01, that is 5 multiplied by 12.01 plus 4 multiplied by 1.01. And when you do the math, you get 64.09 gram per mole. And then remember your formula, N equals molar mass of your molecular formula divided by molar mass of empirical formula. So N equals 128.16 gram per mole. Oh, sorry. Oh, yes. Yeah. Divided by 64.09 gram per mole. And when you do the math and then round the number is like 2. So if you had like 128 divided by 64, that would be exactly 128. So this number is basically rounded. So let me just tell you the exact number so prevent the confusion. When you do this math, you get this number. I just wrote the number from the book previously, but I'm going to just write it exactly as it is. So you get this number. So you should round it to the whole nearest number, which is like, or like nearest whole number, which is like 2. So you say, you write molecular formula equals C5H4 multiplied by 2, which would be like C10H8. So this is that. So another example. Suppose we want to find the molecular formula for fructose, a sugar found in fruit, from its empirical formula CH2O and its molar mass 180.2 gram per mole. So what you do, you calculate molar mass of empirical formula, which is 1 multiplied by C plus 2 multiplied by H plus 1 multiplied by O. And that is 12.01 plus 2 multiplied by 1.01 plus 1 multiplied by 16. And you know, you go to the back of your book or periodic table, write these numbers. And then when you do that, you can also, know that roughly what this number would be. Like, 12 and 16 would be 28, and then this number would be 30 something. Exactly would be 30.03 gram per mole. And then N is like molar mass of molecular formula that you are given, like 180.2 molar mass of molecular formula, divided by molar mass of empirical formula, 30.03. This is gram per mole, this is gram per mole. So when you do this, I'm just going to do that real quick. You get 6.000, which is 6 basically. So your molecular formula would be, I'm just going to go a little upper so I can write more easily. It's like empirical formula multiplied by N. So basically, molecular formula equals CH2O multiplied by 6, which is C6H12O6. So I'm just gonna have the lecture being as like 58 minutes. Don't go over that, but feel free to email me if you have any questions or concerns.